Welcome to another episode from the Veterinary Research Channel. Today, we delve into the fascinating world of veterinary cardiology and explore how cutting-edge technology is being developed to improve diagnostic accuracy. We will be discussing a research article titled Automated Echocardiographic Left Ventricular Dimension Assessment in Dogs Using Artificial Intelligence, Development and Validation, published in the Journal of Veterinary Internal Medicine in 2024. This study, conducted by Catherine C. Stoll and a team of collaborators from various institutions across the United Kingdom, Italy, and Spain, investigates the potential of artificial intelligence to automate the measurement of left ventricular dimensions in canine echocardiograms. Echocardiography, an ultrasound of the heart, is a crucial tool in veterinary medicine for assessing cardiac health and diagnosing various heart conditions in dogs. Measuring the size and function of the left ventricle, one of the heart's main pumping chambers, is a fundamental aspect of this diagnostic procedure. These measurements, such as left ventricular wall thickness and internal diameter, provide valuable information about the heart structure and performance. However, there are challenges associated with obtaining these measurements. Currently, there are no standardized guidelines on how these measurements should be performed in veterinary echocardiography. Veterinarians may use different ultrasound views, such as two-dimensional or motion mode, and different axes, like long axis or short axis, which can lead to variability in measurements. Furthermore, the interpretation of echocardiographic images and the precise placement of measurement calipers often rely on the experience and skill of the individual performing the examination. This inherent subjectivity can affect the accuracy and consistency of measurements, potentially impacting diagnostic confidence and the monitoring of disease progression. Recognizing these limitations, the researchers in this study explored the application of artificial intelligence, or AI, to automate the process of measuring left ventricular linear dimensions in dogs. The hypothesis of this research was that a specifically designed neural network could be trained to accurately measure these dimensions from echocardiographic images of dogs. The potential benefits of such an automated system are numerous. Firstly, AI could potentially improve the accuracy and reproducibility of echocardiographic measurements, reducing the variability seen with manual methods. Secondly, automation could lead to reduced scan times, making the diagnostic process more efficient. Thirdly, it could lower the level of expertise required to perform these measurements, potentially making this valuable diagnostic tool more accessible. Finally, automated systems could improve the efficiency of repeat measurements, which are often recommended for monitoring cardiac conditions over time. While AI has shown promise in automating diagnostic imaging analysis in human medicine and, to some extent, in veterinary radiology, its application in veterinary echocardiography has been limited. In fact, a review of peer-reviewed studies since 2015 found that none had used AI to evaluate echocardiographic images prior to this research. Therefore, this study represents a significant step forward in exploring the role of AI in this critical area of veterinary diagnostics. The researchers aim to objectively assess this technology to evaluate its potential for integration into mainstream veterinary practice. To develop and validate their AI system, the researchers employed a rigorous methodology involving a large dataset of canine echocardiograms and the expertise of numerous veterinary cardiologists. The study involved several phases, including the extraction of training images, the labeling of key anatomical points on these images by experienced echocardiographers, the training of the AI network to learn from these labels, and finally, the validation of the trained AI's performance on a separate set of images. The training dataset consisted of over 1,000 frames extracted from hundreds of canine echocardiograms obtained at a specialist veterinary center. For each study in the training set, a specific ultrasound view, the right parasternal 4-chamber long axis view, was used. This view is often the initial view acquired in canine echocardiography and provides an immediate impression of the heart size and function. Each frame in the training dataset was labeled by one of 18 echocardiographers who marked the anterior and posterior points of the interventricular septum, the wall separating the two ventricles, and the free wall of the left ventricle. To ensure a robust evaluation of the AI's capabilities, a separate validation dataset was created. This dataset comprised 50 additional echocardiograms from the same center, from a distinct time period to ensure the AI was tested on unseen data. From each of these 50 studies, both the end diastolic frame, representing the heart at its maximum relaxation and filling, and the end systolic frame, representing the heart at its maximum contraction, were selected. Crucially, these 100 frames were annotated twice, blindly, by a team of 13 independent veterinary cardiology experts. This process resulted in 26 measurements of each site on each frame, providing a rich source of expert opinions to serve as a benchmark for the AI's performance. The researchers defined the gold standard, or reference value, for each measurement on each image as the average of these 26 expert opinions. The AI network itself was designed using a well-established architecture known as UNet, and it was trained to predict heat maps indicating the location of the 4 key anatomical points, the anterior and posterior aspects of the septum and the free wall. The network was trained over 200 cycles using a powerful computing cluster. During training, various techniques were employed to improve the AI's learning and generalization abilities, including image augmentation and the application of a biological constraint in the form of a pseudo-line to encourage consistent alignment of the measurement points. Once the training was complete, the AI's performance was evaluated on the external validation dataset by comparing its measurements to the consensus of the 13 experts. The researchers quantified the AI's accuracy by calculating its deviation from this expert consensus. To provide context for what constitutes acceptable variation, they also calculated the deviation of each individual expert's measurements from the same consensus. By comparing the AI's errors to the spectrum of errors made by human experts, the researchers could determine whether the AI's performance was comparable to that of experienced professionals. Now, let's turn our attention to the results of this groundbreaking study. The validation dataset, consisting of 50 canine echocardiographic studies, included a variety of breeds and sizes, ranging from a tiny neonatal pug to a massive St. Bernard. This diversity ensured that the AI was evaluated on a broad spectrum of cardiac anatomies and image qualities. The researchers compared the deviations of the AI's measurements from the expert consensus to the deviations of the individual experts' measurements from the same consensus for the interventricular septum, the left ventricular internal diameter, and the free wall, both at the end of diastole and the end of systole. For the interventricular septum in end diastole, the average deviation of individual expert opinion from the consensus was 0.12 centimeters, while the AI's average deviation was 0.11 centimeters. Statistical analysis showed no significant difference between these deviations, indicating that the AI's consistency in measuring the septum during relaxation was similar to that of the experts. When measuring the left ventricular diameter at end diastole, the average expert deviation from consensus was 0.20 centimeters, and the AI's average deviation was 0.13 centimeters. Again, there was no statistically significant difference in the variability of these measurements between the AI and the experts. For the free wall thickness at end diastole, the expert's average deviation was 0.20 centimeters, while the AI's was 0.13 centimeters. In this case, statistical analysis revealed that the AI's deviations were significantly smaller than those of the individual experts, suggesting a higher level of consistency in the AI's measurements of the left ventricular free wall during relaxation. Looking at the measurements taken at the end of systole, when the heart is contracted, the results were also compelling. For the interventricular septum in end systole, both the individual experts and the AI had an average deviation of 0.16 centimeters from the consensus, with no significant difference between them. Similarly, for the left ventricular diameter at end systole, the average expert deviation was 0.25 centimeters, and the AI's average deviation was 0.25 centimeters, with no significant difference observed. For the free wall thickness at end systole, the expert's average deviation was 0.17 centimeters, and the AI's was 0.14 centimeters, again showing no significant difference in the variability of measurements. In addition to comparing the variability of measurements, the researchers also assessed whether the AI exhibited any systematic bias, meaning whether its measurements consistently tended to be higher or lower than the expert consensus. The analysis revealed small but statistically significant positive biases for diastolic interventricular septum, diastolic left ventricular diameter, and systolic interventricular septum, with the AI tending to report slightly larger measurements, by approximately 0.05 centimeters on average, compared to the experts. However, the researchers noted that the magnitude of these biases was similar to the level of deviation observed among individual experts, suggesting that these small biases did not necessarily invalidate the AI's performance. Visual representations of the AI's measurements alongside the individual expert measurements further illustrated the AI's performance. These plots showed that the AI's measurements generally fell within the range of values provided by the 13 experts. Notably, the AI tended to select measurement locations that were near the center of the range of positions chosen by the different experts. And in no instance did the AI choose a measurement point that was more apical or more basal than all the expert opinions. However, the researchers also highlighted some instances where the AI made errors, such as taking a potentially inappropriate diagonal path across the left ventricle or potentially mismeasuring wall thickness. Although they also acknowledged that there was considerable variation among experts in these specific cases, indicating the inherent difficulty in these measurements. Now, let's delve into the discussion of these findings and their implications for the future of veterinary echocardiography. This study provides compelling evidence that an artificial intelligence network can be successfully trained to measure linear dimensions of the left ventricle in dogs from echocardiographic images, with a level of performance that is essentially indistinguishable from that of experienced veterinary cardiologists. This is a significant achievement, demonstrating the feasibility of using AI to automate and potentially enhance this crucial diagnostic procedure in veterinary medicine. The success of this project highlights the power of collaboration among veterinary professionals, even across geographical boundaries. The online platform used for image annotation allowed experts from different countries to contribute their knowledge and expertise to the training and validation of the AI system. This collaborative approach not only facilitated the development of the AI, but also underscores the potential for shared resources and expertise within the veterinary community. The demanding nature of the validation process, where each of the 13 experts labeled 200 image frames, provided two key benefits. Firstly, combining a large number of expert opinions, especially when each expert provides multiple assessments, leads to a more robust and reliable consensus standard against which the AI's performance can be judged. The more expert opinions included, the less likely the reference standard is to be influenced by the individual biases or inconsistencies of a single observer. Secondly, systematically collecting expert opinions establishes a trustworthy scale for evaluating the performance of an AI measurement system. This allows for the setting of performance targets, such as requiring the AI to agree with the consensus at least as well as a certain percentile of expert performance. This approach also inherently allows for a stricter evaluation of the AI on straightforward images where experts show high agreement, and a more lenient evaluation on challenging images where even experts may have differing opinions. The researchers acknowledged that there is currently a lack of established consensus within veterinary echocardiography on the optimal methods for measuring left ventricular wall thickness and internal diameter. This lack of standardization likely contributes to the variability observed even among experienced echocardiographers in their choice of measurement sites. The methodology employed in this study, which involves capturing and analyzing the opinions of multiple experts, could serve as a valuable tool for establishing such a consensus and informing the development of future clinical guidelines in veterinary echocardiography. Furthermore, the researchers suggest that repeating this type of study after the publication of standardized guidelines could yield different and potentially more consistent results. The creation of a curated dataset of echocardiographic images with corresponding expert annotations is itself a significant contribution of this research. The researchers have made this dataset, along with the associated code, freely available to the research community. They believe that such datasets are invaluable for guiding the development of AI systems in veterinary medicine and for demonstrating to trainees where variation in measurements is acceptable and where it is not. These resources have the potential to be used not only by researchers working on AI, but also by educators training future veterinary clinicians. The study focused on the right parasternal four-chamber view, even though many veterinarians typically prefer the short-axis view for measuring wall thickness and left ventricular internal diameter. The researchers acknowledged that measurement variability might be lower in more familiar views. However, they argue that this does not fundamentally alter the conclusions of the study, as the challenges faced by human experts in interpreting and measuring from the four-chamber view would similarly affect an AI trained by them. While the AI's overall performance in terms of deviation from the expert consensus was comparable to that of individual experts, The detection of small positive biases in some measurement highlights the importance of rigorous testing of automated systems on realistic sets of images and the necessity of using an expert panel to establish a reliable reference standard. Even though the magnitude of these biases was within the range of inter-expert variability, it underscores the need for careful validation to ensure the clinical utility and reliability of AI-powered diagnostic tools. In conclusion, this study successfully demonstrated that artificial intelligence can be trained to perform core echocardiographic measurements in dogs with a level of accuracy and consistency similar to that of human experts. The researchers recommend that utilizing a multi-expert consensus is a best practice for defining a reference standard when evaluating the performance of AI in medical imaging. They envision that AI systems have the potential to streamline the workflow of veterinary experts and to improve the uniformity of clinical practice standards. For such systems to gain widespread adoption, the researchers emphasize the importance of transparency, with publicly accessible methodologies and open validation processes overseen by named experts. Thank you for listening to the Veterinary Research Channel. A link for the reference paper is in the video description. Remember to test your knowledge by answering the questions in the description, and as always, keep those minds inspired, hearts light, and tails wagging.